Hi all again. So in this video, we introduce the computation of the Mz-Criterion on three-dimensional velocity data. So the Mz-Criterion is a bit more involved compared to the two-dimensional case. So the theory behind that is exactly the same. However, it is computationally a bit more involved because one needs to evaluate this in three dimensions. And in two dimensions, we made use of the fact that the eigenvectors of a symmetric matrix can be written out precisely, whereas in 3D, such closed form solution no longer exists. And hence one needs to numerically compute them. We will focus, so we'll compute the Mz-Criterion on the steady BC flow, and just briefly recall what this Mz-Criterion is actually all about. So again, we have the steady BC flow with the standard parameters. We start by importing data and by then subsequently interpolating the velocity field. Again, we will compute the Mz-Criterion on all the 6 faces of the cube essentially. So basically on the XY plane, on the YZ plane, and on the XZ plane. The Mz-Criterion is, so the formula for the Mz-Criterion is the same one as the strain acceleration tensor that we will compute it is exactly the same as in the two-dimensional case. So this is unaltered. Of course, now the rate of strain tensor and the gradient of the velocity are no longer 2 times 2 tensors, but they are 3 times 3 tensors. So we start by computing the strain acceleration tensor, which is an objective quantity, along every trajectory launched from a certain position x0 over some time interval t0 to tn. Then we compute, so we define the zero strain set. So the zero strain set in 3D is no longer triangle, but it will essentially be a cone. And I invite you to check out the corresponding paper, which you can find in the references, to see to have a look at the theory behind it. How essentially we need to do 2 things. We first need to compute the strain acceleration tensor, and then we need to compute the zero strain set. And then we say that a trajectory at time t is hyperbolic if the restriction of the strain acceleration tensor to the zero strain set is positive definite. Note that not the whole, it's not that the strain acceleration tensor needs to be positive definite. No, just the restriction of the strain acceleration tensor to the zero strain set. Otherwise, if Mz is indefinite, so basically if the restriction of the strain acceleration tensor to the zero strain set is indefinite, then it is in an elliptic flow region. So hence we distinguish between elliptic and hyperbolic flow regions in this case here. Again, I repeat, it's important that we consider the restriction to the zero strain set, not the positive or indefiniteness of the strain acceleration tensor in general, but just restricted to the cone, so basically to the zero strain set. Evaluating this in 3D is a bit problematic, I would say. So it's computationally not trivial and might also be very costly. However, a major simplification was derived. In fact, in order to check whether Mz is positive definite, we simply need to take a look at this quartic equation. So Mz is positive definite if and only if the quartic equation defined here has no zeros in the time interval -1, 1. The coefficients, so of course, whether it has zeros in this time interval or not, needs to depend on the coefficients. So the coefficients A, B, C, D are given here. So I highlight here. I will not go through all of the individual steps because it's fairly involved. But they are essentially, so one can write down expressions for these coefficients. In fact, that's what we will also do. So we'll compute these coefficients here, and then we simply need to check whether the quartic equation here. So for every trajectory at every point in time, we need to compute these coefficients, and then we need to check whether this quartic equation has zeros in this time interval. If it has no zeros, then MZ is positive definite, and the trajectory is for the moment in a hyperbolic flow region. Whereas if it has zeros in this time interval, then it is indefinite, and the trajectory is in an elliptic flow region. As you can see, all of these parameters are fairly involved. So we start actually, so one of the major steps is that you define the coordinates here, and the eigenvectors EI of the rate of strain tensor and the eigenvalues SI of the rate of strain tensor, they are ordered in such a way. So basically, if S3, so if the absolute value of S3 is bigger than S1, then this value A, which is a geometric quantity related to the cone for the zero strain set, takes this form. On the other hand, if the absolute value of S1 is bigger than the absolute value of S3, then A takes the other form. So basically, you need to flip then the numerator and the numerator and the denominator. And then, of course, you need to also change the way you define this eigenbasis E. So you can see here it is defined in increasing order, whereas here it is defined in decreasing order. These are just little technical things which one needs to take care of during the computation. Once you have defined this eigenbasis, this A matrix, and of course computed the M matrix, then we compute the M, so the strain acceleration tensor in the eigenbasis E, which of course now depends whether it's this one or this one. And then we can evaluate all these coefficients, where MI3 is simply the where these sub-indices simply denote the eigen. So the sub-indices of this M tilde matrix simply denote the position. So simply not the individual elements of M tilde. And of course here it needs to be corrected to this one, of course. Okay, so that's pretty much it. That's just a bit lengthy because it's you need to have you need to define a lot of coefficients. The end statement here is that we compute these coefficients here at each point in time along a trajectory, and then we check whether this quartic equation here has zeros in this time interval or not. Again, we do this. So when we compute the trajectories and compute the strain acceleration tensor along the trajectories, we first compute them for the XY plane, then for the XZ plane, and then for the YZ plane, actually. We have, of course, various functions. So one function is this compute ABCD, which simply computes these coefficients. And it takes, of course, as input the small a value, then, of course, the strain acceleration tensor and the eigenbasis. These are simply the formulas for the coefficients. So this section here simply corresponds to this part here. And then this function here takes as input all the coefficients A, B, C, D, and simply numerically checks whether the quartic equation has some zeros in this time interval, in the time interval -1, 1. The main function here is tau hyperbolicity ellipticity, which essentially computes the time spent in hyperbolic or elliptic flow regions. And we start, of course, by integrating the trajectory. Then we define arrays which store whether the particle is in hyperbolic or an elliptic flow region. Here we iterate over all times along a trajectory. And we simply need, of course, the gradient of the velocity field. We need the rate of strain tensor. We need the gradient of the velocity field at the time step t plus delta t, so at the subsequent type step, because we need to compute the derivative of the rate of strain tensor, which is done here. So this is simply ds dt. And then, so this is not the derivative. So this is simply the rate of strain tensor at the time step t plus delta t. And here we simply compute. So in this for loop, we iterate over all times. And in this for loop, we iterate over each trajectory. What we do here is we simply then, of course, do the compute the eigenvalues and eigenvectors of the rate of strain tensor. for the specific trajectory. Then based on the eigenvalues and eigenvectors, we can then compute these this A value here, small a value here, and the eigenbasis. Here we compute the strain acceleration tensor. Here we compute the coefficients. Here we check whether the coefficients lead to zeros in the time interval -1, 1 in the quartic equation. If quartic equation has a 0, then the particle is in an elliptic flow region. So if bool 0, if this function here returns true, it means that the quartic equation has in fact zeros in this time interval, and hence the particle is for the moment in an elliptic flow region. If it is not 0, then it returns false and the particle is in a hyperbolic flow region. Then, of course, we compute the average time spent in such a region, in hyperbolic and in elliptic flow region, and we return this to this main script here. Then, of course, we need to compute the time spent in hyperbolic and elliptic flow regions for the initial conditions, but with respect to a mesh grid. So here we just simply reshape it to a mesh grid because initially, of course, everything has been vectorized and put into batches so that we can do the parallel computation. The same is done also for the XZ and YZ plane. We can now visualize the time spent in hyperbolic flow regions. You can see that in these areas here where we had these vortices also shown in the LEVD field, the time spent in hyperbolic flow region is 0. So this highlights that these are not hyperbolic flow regions. However, in this area, in these areas in between, these are hyperbolic flow regions and also coincide with ridges of the FTLE field. One can then, of course, also visualize the time spent in elliptic flow region, and you can see here, particles here spend all the time in elliptic flow regions, and hence this is an elliptic flow region. It's like the interpretation of this result is actually very, very straightforward. With that, I invite you to check out the papers and the references, and I look forward to the next video. So here, in the next video, we will essentially compute. We will be dealing with Poincare maps and see how we can use Poincare maps to visualize transport barriers in 3D.